At this part of circular motion unit, we're going to look at some calculations. We're going to be solving for linear and angular speeds. So we're going to look at them both mathematically and conceptually. So let's start off with rotational speed. So this is what we're talking about, circular motion. We're going to be talking about linear speed and rotational, sometimes referred to as angular speed. So here we go. If we look at this in terms of linear speed, we could say, well, okay, it traveled some distance from here to here, or from here to here, in some unit of time, right? We'd say the linear speed is the distance traveled per unit time. But the angular speed is the amount that an object in circular motion spins per unit of time. Angular speed can be described as either the rate of revolving or the rate of rotating. So angular speed works for an object that is rotating, such as the wheel, or something that is revolving. So once again, we're going to use angular speed a couple different ways. So calculating angular speed. So the common units are RPMs, right? Rotations per minute or revolutions per minute. And sometimes it can be defined as degrees per second as well. So angular speed is going to be the rotations or the degrees divided by the unit of time. So let's do a practice. Let's just make this simple. Example, a merry-go-round makes 10 rotations in 2 minutes. What is its angular speed in RPMs? Well, let's see. If it makes 10 rotations, right? 10 rotations in 2 minutes, divided by 2 minutes, it's going to have an angular speed of 5 rotations per minute, or 5 RPM. So let's look at angular speed, right? Angular speed can also be in degrees per unit of time. So let's say that we're measuring, we'll have a CD. Say this is rotating here. So a full rotation is 360 degrees, right? That's a unit circle. So let's say that a bowling ball rolls at 2 rotations per second. We go bowling. What is its angular speed in degrees per second? Let's say if it makes 2 rotations in 1 second, and when I know that there's 360 degrees in one rotation, I can notice my rotations cancels out rotation. 2 times 360 is 720 degrees per second. So my angular speed in degrees per second is 720, right? 720 degrees per second. Well, now let's start looking at linear speed. We need to make sure we understand the calculation of what it, let's just think about what its circumference is. Circumference is a distance around the outside of some circle. So the distance traveled during one revolution equals the circumference of the circle. And we can calculate this. So circumference is going to be 2 times pi times r, where r is the radius. Remember, diameter is bisects the entire circle. Radius is 1/2 the diameter. So make sure we don't get that confused, because I'll be asking you questions where you'll have a diameter and you'll need to find half of it first. So circumference is 2 pi r, right, around the outside of the circle. So let's make sense of this scenario here, determining the angular speed. So remember, let's not ignore that circumference is around the outside, and we can calculate it as 2 pi r. So here we go. So observe the turntable rotating. Notice this here is rotating clockwise. Right? It's kind of misleading here, because here it says it's moving clockwise, but yet here it looks counterclockwise. So let's not overthink it. So see the ladybugs on the turntable. Here's a ladybug, here's a ladybug. So there are 2 of them. One of them is closer to the center. Ladybug fast, we'll call it. And the other one's further from the center. Twice as fast, or faster. Their angular speeds are the same, but their linear speeds differ. So angular speeds. So if this makes 1 full rotation, right, and they're both next to each other, they both make 1 full rotation together, or in this case, sorry, clockwise. I'm using this diagram, this picture here. So they would both end up at the same location after, let's say, 1 second. Let's say they move around 1 time, they would have 1 rotation per second. However, their linear speeds are going to differ, and here's why. Because if you look at the size of the circle, right, the circumference of the ladybug that's closer, it's a smaller circle. Therefore, smaller circumference is a smaller distance traveled in the same unit of time. So this inner one is actually traveling slower than the outer one, that their linear speeds are going to differ. Right? The one further travels a larger circumference. Look at this picture here. Larger distance. Same amount of time. Is traveling faster. It traveled a greater total distance. So its linear speed is going to be greater. Their angular speeds are going to be the same. So the greater the circumference, meaning the further from the axis of the revolution, the faster the object is traveling. So let's look at that a different way. So I'll give you a little different scenario. So determining angular speed. So once again, circumference, right, the distance we're looking at is going to be 2 times pi times r, where r is the radius. Okay, consider a student in his angular and linear speed. So here's a student on merry-go-round. If another student were on the merry-go-round that's closer to the center, so we'll put them here, like right here on this edge. We've got student in orange shirt, and we have student here, we'll call him the imaginary student right here. Closer to the axis of the revolution. So who has a greater angular speed? Well, they'd have the same, because if they're both standing along the same line right here, if we can imagine this line between the yellow and the blue, and this moves here counterclockwise and makes one full rotation, they would have both traveled 360 degrees in the same unit of time. Or they have both made one rotation in whatever that time unit was. So the same angular speed, but their linear speeds are going to differ. Because the kid in the orange shirt is going to travel a greater circumference and thus a greater distance. So a greater distance, oops, right here, if you're traveling a larger radius, you're going to have a larger circumference. That's a greater distance here. So they're going to have a greater linear speed than somebody standing closer. And last but not least, calculating linear speed. So this one will take a little bit of practice, but I'm not going to beat you up with this. You'll probably get one, and I think you'll have it after a very short amount of time. So linear speed from angular speed. So the linear speed we're going to measure in meters per second. So the linear speed is going to equal 2 times pi times r. So essentially you're looking at circumference here. Circumference times the number of rotations divided by the unit of time as a measurement of seconds. So you might say, well, geez, there's a whole lot going on. Okay, well, let's look at it this way. So the blades of the ceiling fan spin at 30 RPM. The fan has a radius of 0.5 meters. Calculate the linear speed at a point on the outer edge of a blade. Okay, so let's do this. So 30 rotations per minute, so 30 RPM, times, there's 1 minute, 60 seconds, so I need to convert minutes into seconds, right, minutes into seconds, equals 0.5 RPS. That's rotations per second. That's key here, because you got to get this in seconds. And then I can solve my linear speed is going to be equal to 2 times pi times 0.5, in this case here, rotations per second. Right? So I have circumference times 0.5 rotations per second. And you'd find that it's about 1.57 or 1.6 meters per second. This will take a little practice. I'll get you some practice with that. So we'll get one more little practice run in here. I want to make sure that you have a chance to practice this. So let's go back to a ceiling fan. So the blades on a ceiling fan spin at 360 rotations per minute. So 360, so much faster than my previous example of only 30. So it's kind of more realistic. They move about 6 times per second. So the fan has a radius of about 0.3 meters, probably more realistic from an average household ceiling fan. So calculate the linear speed at a point on the outer edge of a blade. Okay, so we know that we're going to get this into rotations per second, because we need to know the number of rotations per unit of time. So it's essentially going to be the circumference times the rotations per second. Notice, it's key here. So we know rotations per minute, and we know that 360 rotations per 1 minute times 1 minute over 60, I can convert rotations per minute into RPS, right? Key, 6 RPS. So I'm going to take the circumference, which is 2 pi r, so 2 times 3.14 times 0.3 meters, times 6 rotations per second, and I'm going to find my linear speed. It's going to be 11.3 meters per second. And once again, it just takes a little bit of practice. There you have it.